Welcome our second speaker, Oscar from KTH. The title of his presentation is Partial Evaluation of Automatic Differentiation for Differential Algebraic Equation Solvers. Let's welcome.
Yes, so my name is Oscar and I will talk about our work on partial evaluation of automatic differentiation for differential algebraic equation solvers. And the outline of my talk is as follows. And I will start with the background and motivation. So equation-based object-oriented modeling is a well-established paradigm for modeling dynamical systems, typically physical systems, which allows rapid modeling of, for example, aircraft, power plants, and vehicles. EUO models are fundamentally described by differential algebraic equations, and a key challenge for EUO tools is that of high-performance simulation. This essentially boils down to numerically solving DAEs, and this is the focus of our work. In particular, we focus on two aspects of DAE solving. The first one is called index reduction, where you sort of transform the DAE into a form that is suitable for an off-the-shelf numerical solver by differentiating the equations of the DAE. And the second part is that of Jacobian evaluation. So the numerical integrator needs to be able to evaluate the Jacobian of the DAE during the numerical integration routine. So we need to also provide a callback function for computing that. So what is a DAE? So we can consider this pendulum in the plane here, and let's say we want to model this using Cartesian coordinates. We can then describe the position of the endpoint of the pendulum arm with the two time-dependent variables x and y here, and then we have an additional time-dependent variable tau, which models the tension per unit length in the pendulum arm. We can describe the dynamics of this system by these two differential equations, and then we have an additional algebraic equation which constrains the position of the pendulum endpoint so that it will only sort of move in a circle around origo in this case. And this last equation is what makes this an DAE as opposed to an ordinary differential equation. So solving DAEs, so if we take this DAE and we rewrite it into a residual form, we just move everything to the left-hand side and write it in vector notation. We can pass this DAE into an off-the-shelf numerical solver given that the Jacobian of the residual function with respect to the time-dependent variables at the highest derivative order is non-singular. And in this case, this is clearly not true because none of these appears in the last expression here. However, we can fix this, and the fixing is what is known as index reduction, where we differentiate some of the equations of the DAE in order to make this Jacobian non-singular. In this case, we time differentiate the last expression twice here, which will reduce the index from 3 to 1. And for reference, an ODE is a DAE of index 0 is in fact an implicit ODE. Then we also typically rewrite this residual function on first order form. And then during the numerical integration, we have to supply to the solver a function to compute this Jacobian, which is just a sum of the two partial derivatives of f with respect to the time-dependent variables and their first order derivatives. So this is what we want to produce. So differentiation in EUO languages, so index reduction and Jacobian evaluation use either symbolic differentiation or forward mode AD. Symbolic differentiation can lead to very efficient code, but if we want to produce a symbolic Jacobian function, we have for a function of n inputs and n outputs, we have to produce n squared partial derivative expression, and this might not be feasible for very large n. On the other hand, AD naturally extends to general language constructs such as recursion and control flow. It's also efficient in computing the AD for this residual function, both in space and time. But when we sort of do the AD computation, we change the elementary operations to not operate over real numbers, but rather over tuples of numbers. So we essentially propagate a function's value and all its derivative throughout the computation. And this leads to some additional overhead because we need to destruct and construct these tuples during the computation. So the question is how we can combine the strength of ST and AD while mitigating their weaknesses. And we propose to use partial evaluation of AD in this DAE context. Partial evaluation of AD has been explored before in the literature, but not in the context of DAEs. And partial evaluation of AD gives a residual program which will then contain, in the general case, both AD and ST. We also propose to parameterize the specialization of the Jacobian function so that the user can trade off between code size and code specialization. In particular, we propose a new transformation method. We call it forward mode PAD for DAEs, and it takes as input a high index DAE program. This DAE program may contain recursive functions, and it then outputs a residual function of low index, and the residual function is made efficient by using partial evaluation. We also output a Jacobian callback function where the user can sort of specialize the level of specialization. And moreover, we implement our approach in the miking framework, which is a framework for composing domain-specific languages, and we evaluate our implementation on a number of non-trivial EO models. And this implementation is available as open source. So if we now move on to the approach. So this figure here gives an overview of our transformation. So the input here is the high index DAE program P. We also have this user parameter phi, which sort of controls the level of specialization for the Jacobian function. And intuitively, phi equals 0 here means that we don't specialize any of the partial derivatives of the Jacobian, while as phi equals 1 means that we specialize all of them. We also have this block SA here, and SA here stands for structural analysis. So there exists efficient methods for sort of computing, determining which equations we need to differentiate in order to index reduce the DAE. And this is not part of our contribution, but we assume that it is present. And for example, the output of this, or we encode the output of this structural analysis as a tuple here, where the elements of the tuple denotes the number of times we need to differentiate the corresponding equations in our DAE.
Just a clarification. So the high index DAE program, that means you have to take multiple times, like partial derivative multiple times to convert it to an ordinary differential equation? Is that what high index mean? Like?
Sorry, can you
repeat?
No,
like what is this quantifier high index DAE program?
It means that we need to, so if we go back.
So you have to take like multiple times to convert it?
No, so you have this, and then you need to differentiate some of the equations of this DAE in order to make it solvable. So you differentiate the equations with respect to time, and that transforms the DAE, the high index DAE into a low index DAE, which you can solve with a numerical solver.
So low index PAE means what? Like, so low index is like the same as ODE?
So the index, you can see the index as a measurement, a distance measure between the DAE and an underlying implicit ordinary differential equation.
Okay.
And those we can solve, but the DAEs of high index we cannot directly solve because this Jacobian here is not, it's singular with respect to the highest derivatives of the DAE.
Yeah.
Is that clear? Oh. So thank you for the question. Yes, so that is the input. So this DAE program may be of high index, as I said. And then we have this sort of structure analysis that tells us how we can transform this into a low index DAE that we can solve. And then we have to just perform this transformation using differentiation of the program. And the output here is then a residual function f and this Jacobian callback function j. Right. So this input program has the following abstract syntax. So it's essentially a sequence of let bindings, either recursive or not, that ends with a sequence of residual expressions that encodes equations. The expressions themselves is the lambda calculus with well-known extensions. And we also extend these expressions with time-dependent variables, where n here denotes the derivative order of this dependent variable with respect to time. And then we use asymptotic sugar this sort of common dot notation to denote time derivatives of dependent variables here. So if we return to our pendulum example here, let's say we set all the constants to 1 here. We also introduce a runtime parameter here for the sake of the example. And then we can write a version of this pendulum model in our high index DAE program as follows. We've also used a recursive power function here for illustration purposes. but we changed this program so that the last residual expression here, sort of the second term there, includes an exponent which is parameterized on this runtime parameter, essentially. And the index reduction transformation, which sort of takes this high index DAE program and turns it into a low index residual function, it's driven by the forward mode AD transformation for higher order derivatives. So in this context, this transformation essentially transforms an expression of type real into a new expression that is the type a tuple of reals, where the ith element of this transformed expression corresponds to the ith time derivative of the original expression. We extend this transformation with the dependent variables, and they transform as you would expect. We simply increment the derivative order of the dependent variable during the transformation. We also have some additional sort of rules for making sure that non-time dependent variables bind to correct expressions in the whole program, but I will omit those details here. So then, given this output from the structural analysis that tells us how many times we need to differentiate the individual equations of the DAE, we can then straightforwardly index reduce our DAE program by just essentially with these three rules. So I will not sort of go into detail here, but the big picture is that we index into this tuple D here, which tells us how many times do we need to differentiate the corresponding equation. We apply the AD transform to that number, and then we project out the corresponding element from this tuple. And for the bindings here, we just make sure that all bindings exists for all derivative orders that we will encounter in a program, and then with a bit of renaming, we make sure that they bind to the correct identifier binds to the correct sort of expression here. So I will go through an example here. So this is the same program we've seen before. So as I said before, the structural analysis will give us this D, which tells us that we need to differentiate the last equation twice with respect to time. So I will focus on that expression only here. So then this sort of index reduction involves transforming this using the script D transform here that sort of applies the normal AD transform that we have extended with support for time-dependent variables. And then we project out the third element here, which will then correspond to the second time derivative of this expression. And if we do this, we get something like this. And you don't have to sort of follow all details here, but the essential part is that we have lifted all the elementary operations in this expression to now propagate both the expression's value alongside with the first and second order derivative of its value. And then this function pow here now is replaced by, the identifier to this function pow is replaced by pow bis here. And then pow bis will be a version of the original function pow, which is also lifted to also propagate first and second order derivatives. So we can improve upon this code by partial evaluation. And here we can note that the first exponent here, the 2, is statically known. But given that the theta here is a runtime parameter, the second exponent is not known statically. So if we apply partial evaluation to this, we will essentially get this, where we, for the first term, unroll the whole recursion, and it will simplify down to a symbolic derivative, essentially. So we have no operations here over this lifted sort of dual numbers, as they're called. But while the second term here instead computes the derivative dynamically using the AD sort of method. And we have implementation that we call PEVAL. It's an online partial evaluator that is based on the ANF transform to preserve sharing. But PEVAL itself is not part of our contribution, but we will use it in the next section when we discuss the Jacobian code generation. So we return to the overview here, and now we'll talk about this part, which is related to generating a Jacobian function. And here we also use some information from the structure of the DAE, so we can know for sure, because we know which dependent variables appear in which residual expression, we know for sure that some partial derivatives in this Jacobian will be identically equal to 0 always, and we can avoid computing those at runtime. And we encode this structure as a sequence of columns, basically, where for each column we sort of save the indexes of the rows in the Jacobian matrix, where we don't know for sure that these elements corresponds to non-zero partial, zero partial derivatives that are identically zero, so partial derivatives that we need to compute during runtime. Then from this index sequence, we can then take our residual function, the low index residual function that we've already generated. We can sort of lift it again using the AD transformation so that it will compute the Jacobian. And then we can construct a Jacobian function that only computes non-zero partial derivatives by essentially folding over this index sequence and computing them given values of the dependent variable and their first order derivatives. And then it returns a sequence sort of encoding a sparse representation for this Jacobian matrix here. So we can then specialize all partial derivatives by just applying our Peval transformation to this Jac function applied to this index sequence. But once again, specializing all partial derivatives might not be acceptable for very large n, as it will lead to a lot of expressions. So we instead propose to sort of divide this index sequence into disjoint sets, if we view it as a set. We are in the first set, which we sort of call index subscript S, where S stands for static. We put all the columns that corresponds to columns in the Jacobian, which has fewer or less, equal or less than phi times n non-zero partial derivatives. And the remaining ones we put in the index set subscript D, where D stands for dynamic. And then instead of sort of specializing all the partial derivatives, we specialize the columns that corresponds to index sets, columns that are in the index set static, and we compute the remaining columns in the Jacobian using sort of the normal AD method. And this instead gives an upper bound in the form of n squared phi here on the number of specialized partial derivatives instead of n squared. Yes, so we move on to the experimental results now. So these tables, the first table shows the models that we evaluate. I will focus on two largest one here. So both of these models are formulated as sort of high-level EO models, and then we automatically generate the corresponding DAE for these models. In the first case, we have a three-dimensional system that contains 143 equations, and these equations are quite large and quite complex, and they're highly nonlinear. And index reducing this model amounts to differentiating 55 of these 143 equations. In the second case, we have a circuit, a linear circuit with a repeated structure. It has quite many equations, 408, but only 2 of these needs to be differentiated in order to index reduce this DAE. And since it's linear, we can also see if we look at the number of, if we compare for S3100 here, if we compare the number of Jacobian evaluation and residual evaluation during the simulation, we see that there are very few Jacobian evaluations, and this is because the solver sort of detects that, okay, this matrix is actually constant, so we don't need to evaluate that many times. And you can compare that to S2, where the solver repeatedly have to evaluate the Jacobian matrix during solving. So essentially, we don't expect to see much improvements for S3100, because, yeah, we will come back to that essentially. So the PED implementation targets OCaml, and it uses the Sundial's IDA solver as a solver backend. And then we measure execution time and executable size over 100 runs. The executable size will increase moderately with increasing level of specialization, so I will not talk more about that. But we will look at some graphs on the execution time for these two models. So for the first, so to read off this, so in the legend here you see 3 different simulation modes essentially. So sim here denotes simulation using the numerical solver, so essentially solving the DAE. Res and Jac denotes evaluating in sort of isolation the residual function and the Jacobian function the same number of times as these are evaluated during the numerical simulation to better sort of separate what contributes to what here in the sort of execution time. On the x-axis, the AD part here, that denotes sort of doing index reduction by automatic differentiation and producing this sort of sparse Jacobian computation using also automatic differentiation, but without any sort of partial evaluation. While PEAD is the sort of our approach which applies partial evaluation, and the number here next to PEAD denotes sort of the level of specialization of the Jacobian function. 0 means no specialization, and the final value means that the Jacobian is fully specialized. And we can see here that we have sort of the larger nonlinear model S2 improves on all aspects for all simulation modes, while as we would expect, the circuit here, since it only involves differentiation of 2 equations, and the Jacobian is not evaluated that many times during simulation, the sort of the improvement, there's no real noticeable, there's no improvement actually here in the simulation time. So to summarize, we've designed a technique for partial evaluation of AD in the DA context. It applies to both index reduction and Jacobian evaluation. And the evaluation shows that it improves the performance of nonlinear models compared to a pure AD approach. And going forward, we would like to sort of combine our approach with the graph coloring approach for sparse AD computation, AD Jacobian computation, and we would also like to extend our index transformation to also include sort of stabilization through a method you can call implicit projection. So that concludes my presentation, and I'm happy to take any questions.
Thanks for the great talk. So in the AD world, there are basically 2 techniques to implement automatic differentiation: forward mode and reverse mode.
Yes.
And usually in many use cases, especially whenever the objective function is like something going from Rn to R, it's better to use the reverse mode AD.
Yes.
So here in this case, why the forward mode AD would be sufficient? Can you give us some insight?
Yeah, because the function that you're computing the Jacobian for is square, basically. So you have the same number of inputs as the number of outputs. So there's no like gain from using reverse mode here. You might as well use the forward mode.
I see. So then it's because basically your Jacobian matrix is
it's square.
Square.
Yes.
Okay, I see. And so if there are no other questions, I have a follow-up one. So can you elaborate a bit on the experimental results?
Sure.
Yeah, this one. Can you tell what is really what does the number specialization level basically mean here?
So it's yeah. So it's sort of the. So yeah, so the exact meaning is you have this user parameter phi. It ranges from 0 to 1, and then you have the size of the Jacobian is n. So you have n rows and n columns in the Jacobian, and the number here after the period is the number m here. So it's the size of the Jacobian times this user parameter phi, and this means that all columns that has non-zero partial derivatives, let's say, they have phi times n or fewer non-zero partial derivatives. Those will be specialized. The remaining ones will be computed using sort of the normal AD approach. Is that understandable?
Is that kind of connected to the sparsity of the Jacobian?
Yes, because we know, so we can know for sure, but since, I mean, in order to do this index reduction, we have to have information on the structure of the underlying differential algebraic equation, so we know which variables will appear in which equations. And this means that we know for sure that some of the partial derivatives will be exactly equal to 0 all the time, so we don't really need to evaluate those. And then we specialize according to this information, so we sort of first specialize columns in the Jacobian matrix which has sort of fewer non-zero partial derivatives, which means that you will get less sort of less expressions. Well, let's say you have this bound that I showed before on the number of specialized partial derivatives in the end. Instead of having it as n squared, you have it as phi times n squared.
Thanks.
Thank you.
I also have a question about the experiment. So this is within your framework, like the comparison entirely, right?
Yes.
So did you? I'm not really sure. I don't really know about the field, right? But are there like other existing frameworks that you may be able to use, like that kind of solve a similar issue? And how does your performance comparing to, say, existing state-of-the-art?
So we haven't compared to other frameworks, and this is because they use different runtimes and so on, and of course that can be interesting in itself, but this is only we only show here essentially that it pays off to partially evaluate this AD transformation here. But of course it's interesting to compare to existing tools, but they employ a lot of other optimizations that we haven't really, done here.
I see. So do you kind of expect that if you run if you just compare with, say, an existing highly optimized framework, maybe you will see, say, similar or even slightly better performance?
Yeah, I would suspect better performance. They are more sort of mature in nature, and they employ other sort of optimizations. So I would say that probably they will outperform us in this case. So this is more of a demonstration of the approach here. So.
But
can you please focus
on sorry. Yeah. Sure. Yeah. But that's actually all. Yeah. Thank you.
Okay. Thank you very much.
Any other questions from the audience? No. Okay.
We have still a bit of time, so I was regarding the same question. So what kind of competitor systems do you have in mind? And I was wondering about so for example, one competitor that I can think of is like TensorFlow and PyTorch, and basically over there then they have some sort of facilities to compute Jacobian functions. But if you wanted to have a kind of tensor format representation for the data, so what are the shapes of the tensor data in each of the benchmarks that you consider here?
The shape of I don't...
Yeah, so for example, whenever we are calling, let's say, in PyTorch, we're calling the Jacobian function.
Yes.
So you have to pass it a function that takes as input tensors, and let's say outputs also a tensor. Let's say it takes a vector as input and a vector as output. So I was wondering, for each of the workloads that you have here, what is the shape of that vector? Is it like 100, like 10, 1 by 10
the shape. So for the for the Jacobian computation, so the brown one, that would be. So you input the states. That's n times, and then in the order here for the experiments, that's a few hundreds, I would say. For the experiments here, up to 400 for the largest one, and then the output is a matrix of n times n size. Essentially, yeah.
I see. And especially for the cases that they are sparse, the Jacobian matrix is very sparse. I don't think that those frameworks are going to do a good job, because those frameworks are meant for dense computations.
Yes.
Especially here, if you're leveraging the sparsity, then I think that you can get some improvement even in comparison with those frameworks.
Yes. Okay. Thank you.
Let's thank our speaker again.